Okay, so I got cut off in the middle of this one, so let me go ahead and continue on with it. So we were talking about how we have a current of 5 amps here and another current of 7 amps here, and we were trying to figure out the total magnetic field in the middle. So magnetic field's a vector, so we have to figure out which direction these two currents' magnetic fields are going, so we'll know if we need to add them together or subtract them or whatever. So if you do the right-hand rule on current number 1, you put your thumb coming out of the page, you curl your fingers around, you'll see that the magnetic field is going in this direction, right, as you do that. So at this point in space, the magnetic field is pointing straight up for current number 1. If you do the same thing for current number 2, but you put your thumb into the page and curl it around, you'll notice that your fingers curl around this way. So that means at this point in space, magnetic field 2 is also pointing up. So that means that when I find both of these fields, I'm going to add them together to get the net magnetic field, because they're both pointing in the upward direction. Okay, so I can find each one of them by doing mu naught, the I of each individual one, times 2 pi, and the R for each one is 5 centimeters away, so 0.05. Okay, that's going to be for the one on the left, the current on the left. You'll do the same thing for the current on the right. Figure out the magnetic field for that one, mu naught I2, you'll do 7 amps for that, and then over 2 pi R for that one, 0.07. My pen just died, so I have to use my mouse, so this is going to be a little tricky. You'll find 2 values for those. You'll add those 2 values together to get your total magnetic field. All right, the last problem has to do with 4 wires. Each of these is a different situation. They want to know, where is the magnetic field greater at the center of the square? Is it A or B? Right, so we're going to look at these. That was a mistake. Let's see if we can get rid of that. So let's take a look at A first. The magnetic field for each of these wires, we have to figure out what direction it is. So if I take this wire as wire 1, put my finger out of the page, his magnetic field goes around in this direction, right? Same thing for this guy. His magnetic field goes in that direction. So if I'm at the center of the square, right at that space, I think about my fingers sweeping around and coming up here, the magnetic field for 1 is in this direction. And if I call this wire 2 right here, his magnetic field, if I think about sweeping around and around and around in that direction, right at the center, his magnetic field is pointing tangent to the circle there. Now these guys, we'll call them 3 and 4. If we think about their magnetic fields, for 3 it comes around in this direction, and for 4 it also comes around in this direction. So if I think about my fingers sweeping around and around and around, and I get to this spot right here, I would have a magnetic field for 3 that would run the same direction as number 1's magnetic field. And if I do the same thing for 4 and sweep my fingers around and around and around, when I get here, this one will run the same direction as 2. So those have magnetic fields, so the net magnetic field is going to be somewhere in this direction probably, something like that. It's a combination of those 2 sets of vectors. Over here, I have a magnetic field for this corner one that's this direction. And for this corner one, the magnetic field at this place, if I swing my fingers around, will be in the opposite direction. So those 2 are going to cancel each other. The same thing is true for these 2. The other corners, they will be in this direction and in that direction. So the net magnetic field in part B is going to be 0 at the center because of the way the charges, the currents are configured. Okay? All right, last little bit is how do we handle the magnetic field around a loop of wire. So if you think about this loop right here, if you put your fingers in the direction on the far side of the loop and swing your fingers around, they're going to go around the wire in this direction, right? So you'll have a field that sweeps around the wire in that direction. And here you'll have a field that sweeps around the wire in that direction. And this will be a field that sweeps around the wire in this direction. So if you add all those up, you end up with a field that comes around the wire and comes back through the other side. And that's what this shows, a field that goes around the wire and comes back through the other side. So if I had over here a loop of wire that current was running counterclockwise, so the current's going this way around the wire, counterclockwise, right? If I take my fingers and I put my thumb in this direction, right at this point, it's going to be running into the page on the outside and coming back out of the page on the inside, right? So into the page on the outside and back out of the page on the inside. Those are supposed to be circles with X's in the middle of them. And then the same thing here, into the page on the outside and out of the page on the inside of the loop. Just like that. So I would actually have a magnetic field on the inside of that loop that would be coming out at me at all places. So I would be creating a magnetic field that's coming out all the places because this current is running in a counterclockwise direction. Oh, and they asked you, I'm so sorry, they asked you to do it with clockwise, so let's do clockwise below, now that I've confused you royally. Actually, let me just do it right here. If the current runs clockwise, then that means the current is running in this direction, right? All the way around. And if I put my thumbs in that direction, my fingers point in on the inside of the loop, and they come out of the page on the outside of the loop. And the same thing here, in on the inside of the loop, and out of the page on the outside of the loop. So that means that the magnetic field for this loop would be in at all places on the inside of the loop, and it would be coming out on the outside of the loop. Now, why is this important? Because a single loop, although it's interesting, is not usually what we deal with. We usually deal with multiple loops, like on the next slide. So when you have multiple loops, it's called a solenoid, when you have many, many, many loops, and that creates a magnetic field that runs all the way down the center of that solenoid and comes out and goes on the other side. So it creates, the solenoid starts to act more like a magnet, a bar magnet, with a north end and a south end, and a nice, strong current magnetic field on the inside of that solenoid. And that is it. So hopefully now you will be able to go do the first 5 problems on that worksheet.